Metamorphic textures are very simple. They're either non-foliated or foliated. And foliations are simply the presence of layers of minerals. Layers may be the wrong word to use, but it is an alignment. So as we can see in these larger samples, we see an alignment of the grains in one direction, and that's due to that directional pressure, that compression that these rocks experienced during their metamorphism. So the foliations that we see in our samples, I've placed them in order based on their degree of foliation. So with number 67 being slate, this has the lowest degree of foliation. It has the lowest metamorphic grade. And the reason why it has those low ends of both of those properties is because it doesn't really take that much heat and pressure to make slate out of a piece of shale, the sedimentary rock shale. So here we see in number 67, our grains are still very small. We have even some of that residual layering that we saw in our shale. And so the grains this is basically just a little bit better put together piece of shale. Still very thin. We still see that property of fissility. So here is a larger piece of slate. So as we rotate it on its side, you can see those foliations. You can see that the pressure was directed like this. We squeezed this rock and those minerals aligned. These minerals are mostly chlorite, and that is most likely what is consisting this particular piece of slate. Now, as we increase the heat and pressure, our slate, the grains within that slate will grow a little bit larger. And we may get some of that chlorite transitioning or recrystallizing into some of our micas, so muscovite and mica. Do you see how this has a sheen to it, but we still are dealing with very small sized grains? That is characteristic of phyllite. So phyllite has a sheen. Sometimes it'll have some ripples in its surface, but not always. And so that very fine grain texture, but with the sheen, is what classifies phyllite. Now, if we crank up the heat and pressure on phyllite, we will get schist. Now, your kit has two different types of schist. We have number 72, which you can tell is green in color. This is a chlorite schist. So this is a very low-end intermediate metamorphic grade because chlorite is mainly a low-grade metamorphic mineral. And so to have it aligned in such a way with these degrees of foliation, to have the chlorite minerals grow to a large enough size to create a schistose foliation, schistosity is how we would classify the level of foliation here. We would need some of that low-end intermediate temperature and pressure. But most of the time, you're going to get number 71. We're going to see the transition from our phyllite, those fine-grained mica grains, they're simply going to grow larger in size to produce the mica schist that we see in number 71. In number 71, we can determine individual flakes of both muscovite and biotite, and that is very common in a schist, a mica schist. Here's another example of a mica schist that has grains of garnet. So when we talk about index minerals, this is an example of a mica schist that has little porphyroblast. We call those porphyroblast. Those larger index minerals embedded within that schist, that schistosity. So those are little garnets. And so by having the garnets present there, we can tell exactly what temperature and pressure this particular schist formed. All right, so let's get real about what my sample for nice looks like. Number 74 is supposed to be nice. If you look closely at my sample, it looks a lot like mica schist. And personally, I mean, I see a little bit of quartz and feldspar mixed in there. Unless I saw a bigger sample of this, I probably would not have called this nice. And I'm going to show you why. Do you see this sample? This sample is nice. And I mean, it's nice and it's actually nice, the metamorphic rock. So you see how we have that banding. We have light and dark banding separating the non-ferromagnesian silicates from the ferromagnesian silicates. It takes a lot of heat and pressure to get the minerals to separate like that. And that is that gneissic banding. This is what makes a gneiss. So when I look at my sample number 74 from the kit, I just don't see that. And so you'll have to take a really close look at your sample to see if it's really kind of on that edge of being a mica schist, because crank up the heat and pressure on mica schist and you start to get things like gneiss. Now here's just some other examples of gneiss. Here we have an igneous component to the gneiss. So remember, as gneiss cranks up that heat and pressure, it's the very end stage, high grade metamorphism. We can actually have some of these non-ferromagnesian silicates, because they are lower on Bowen's reaction series. They can actually begin to remelt during metamorphism. And when they do, they create that magma that can then re-solidify within the gneiss. And that's what we have happened. That's what happened right here to create this seam here within the gneiss. We had a little bit of remelting and resolidification. So this particular sample may, in certain circles, be classified as a migmatite.